to optimal solution for subproblems, right? So you need to be able to reason about the relationship between the optimal solution for subproblem and optimal solution for the entire problem. Okay. And we gave this knapsack example, in particular fractional knapsack. Fractional knapsack has a pretty solution, but 0-1 knapsack is self-incomplete, right? So we can't do that. So then we looked at spanning tree, which is a very interesting and very useful algorithm. And one of the things I do expect you to know is when it is applicable, right? So you can be almost certain that there will be some problem in your exam that either the midterm or the final that's going to be about spanning trees and recognizing where spanning tree is applicable, right? I'm obviously not going to ask you, given this graph, construct a spanning tree, right? I mean, maybe I'll ask, but that's somehow not the interesting problem to ask. And then if I did ask, then I'll give you 2 points for that. It's not going to be a big problem, right? So a more involved problem would be one where you need to recognize that this is an instance of minimal spanning tree problem, right? So that's and it's not very hard, right? We already gave some examples. So, right. So, for instance, these are some canonical examples, right? So, what I'm trying to say is that spend a minute at least on thinking about each of those examples and why minimum spanning tree is applicable there. And if you did that, then you will be able to recognize another problem where minimum spanning tree is applicable, right? So that's all there is. Sometimes we tend to sort of look through the algorithms and then say, okay, once we are done, that's it. But that's not what I want you to do. I want you to also think about what it means and where it is applicable. Okay. So Kruskal's algorithm itself is quite simple, right? So it basically picks the edges from minimum to maximum, right? And it will pick that edge if it's useful, which means that it's connecting two parts of the graph that are not yet connected. Then you will keep it. If it's not useful, in the sense that it's connecting two nodes that are already within a connected component that you have built so far, well, then you just discard it and go to the next one, right? So the algorithm couldn't be simpler, right? It's just the most, the simplest algorithm that one could think of, right? And it ends up working, which is sort of the beauty of the whole problem and the algorithm. And such a simple algorithm also has such a wide range of applications. That's really interesting. Okay, and one of the things we did do is we didn't really tell you how to figure out whether two vertices are in the same connected component or not. So this is called disjoint set union problem. Okay, we'll come to that much later. It's one of the most interesting algorithms that we will. Well, all algorithms are interesting, but it is also somehow very interesting because when we get there, you'll see why I call it interesting. But without knowing exactly how to do it, we can understand the concept. So that is, what is a disjoint set data structure, right? So in a disjoint set data structure, you are able to ask, right? Given an element X, you can ask what set does it belong to? Okay? So because the sets themselves are disjoint, right, this answer is uniquely defined, right? Each element belongs to exactly one set. Okay? So you want something that answers this question of what set does the element belong to very quickly. Okay? Of course, you could do this in linear time and so on, right? Because you can just look through all the sets that you have and search through them, and there are only a linear number of elements across all of those elements, all of those sets. So you'll definitely find the answer in linear time, but the question is, can you do it faster? And there are techniques for doing it in log n time and also essentially constant time. Okay, so that's the part that's most interesting. How can you do this in a constant time? Now, once you can figure out what set an element belongs to, then you can answer this question of, do they belong to the same component by saying, okay, give me the set to which one of these vertices belongs. Give me the set to which the other vertex belongs, and then the set happens to be the same. That means they are both in the same connected component. Okay. Now, on the other hand, if I am adding an edge, right, that means that corresponds to making a union of sets, right? Because each connected component is being represented by a disjoint set. Okay? So whenever I add an edge between two connected components, that amounts to taking the union of the two sets. Okay? So if you have a data structure that gives you fast unions and fast set identification, right? That is, given an element, identify the set that it belongs to. If those two operations can be done fast, then this whole algorithm can be completed in very quickly. So if you so you should know what is the complexity of this algorithm. That depends on what data structure you use for disjoint set union, right? So depending upon what you use, if you use something that requires log n time, then you'll have one complexity. If you have something that takes essentially constant time, then then you have this loop and you have this delete min, right? So you end up spending essentially n log n time, right? Because this delete min takes it takes time that's logarithmic in the number of edges, right? And we have said log e in a graph is same order as log v. So therefore this one only takes log v, and then if this takes constant time, then log v times the number of times this can be iterated is this is going to be e, right? So I made a mistake. It's not n log n. So because you may have to go through every edge before you get to the complete the graph. So you have you may end up spending e log v time. Okay. Now technically it's not e log v. There is still some non-constant quantity that comes in, but for all practical purposes you can assume that is constant, because the non-constant grows to 3 or 4 by the time you have a number like trillions. So it's really not something that you need to worry about. So then, as a second example of a greedy algorithm, we looked at Dijkstra's shortest path. And remember that. So somehow, one of the things to remember is that the reason why we compute shortest path to every vertex instead of computing shortest path between two given vertices is that we don't know of a good solution to that can tell you the shortest path between two vertices without possibly looking at every vertex in the graph. Okay, so that's why we often end up doing either single source all destinations, right, or all pairs of sources and destinations. Those are the two types of graph shortest path algorithms we discuss. We don't discuss shortest path between two given vertices because there isn't any good way to solve that problem. Okay, so again, shortest paths obviously have many applications, just like spanning trees. Shortest path problem arises in many important context. And once again, just as I said about spanning tree, I would expect you to be able to recognize situations where shortest path problem is really what you need to solve, and then say, okay, I'm going to apply this. So again, I'll never ask you to, unless I ask you explicitly to write Dijkstra's algorithm, you would never have to say anything beyond, okay, I will use Dijkstra's algorithm and it has this complexity, right? So that's, so often the solution, right? I mean, the solutions will often be your solutions if you think through the problems well enough, right? Should generally be much smaller than the problem, right? Because the problem I have to explain and try to make sure that there isn't any ambiguity and it's clear and so on. But you generally, the solution is actually much easier. So don't try to write something very long and complicated, because I do have limited capacity in terms of being able to understand. So if you write a lot, it's a lot harder for me to figure out than if you write a small amount. But if you find that you really have to write a lot, then give me a roadmap, right? So say, I'm going to do steps A, B, and C, and now expand A, B, and C, then I have some chance of actually understanding what you're trying to do, and therefore give you, appropriate credit, right? Because otherwise, it's not to your advantage to lose credit simply because I don't understand your solution, right? So try to make it easy for the reader to understand what you're trying to say. Okay, so one of the other things that we talked about repeatedly is how to prove these greedy algorithms are correct. And there is a familiar exchange algorithm which says, you say that you have a better algorithm, give me that, and I'll tell you how to construct an even better solution, and therefore, your contention that you had a better algorithm was completely wrong, right? So that type of a proof we have in every example that we have studied in greedy algorithms, and therefore that's something that I want you to look at and be aware of, so that if in case I ask you, these days I generally don't ask too many proofs, because I find that students don't go through, we don't emphasize theory as much as we used to do many, many years ago, and as a result, for the instructors, it is very easy to expect that you should be able to do the proofs very quickly, but for the students, it seems that it is not that easy. So what I try to do here is that even though I have the proofs and so on, what I'm really looking for is for you to understand really the underlying reason. So even if your proof is not watertight, if you really understand why something is true and you're able to convey that, then that's really what I'm looking for, instead of looking for a really totally correct and formal proof. Okay, so we looked at Dijkstra's algorithm and some examples, and its complexity. I feel that we don't have to go through this in detail, especially because we are coming back to shortest path algorithms. That's how we are going to finish out the dynamic programming unit on Tuesday, right? So I don't want to go through this again. But if you have any questions, of course, feel free to ask. And then, as a third example, we looked at information theory and coding, and in particular Huffman coding. And once again, this is a very, very nice algorithm, because someone comes up with a fundamental result about coding and saying that doesn't exist a better way of coding than this. And then, soon after, soon is like 10 years, maybe not so soon, but the fact is that somebody comes up with a very nice algorithm, and a very, very simple algorithm for creating codes that actually reach this lower bound. Right? So, and the algorithm is also extremely simple, and has a simple recursive structure where you make a greedy choice by looking at the two least frequently occurring symbols, and then you combine them, and then now you're left with a problem of size n minus 1, right? So you have n points, n symbols to start with. You pick the 2 least frequently occurring symbols, and then you construct this, and now you treat the combination of these 2 symbols as if they are 1 symbol. So instead of having n symbols, now you have combined 2 of them into 1, therefore you have n minus 1 symbols. And so you simply reapply the algorithm to this n minus 1 collection. And so it's a simple recursive algorithm and ends up computing optimal cores. So, and then we talked about what it means in practice, because in practice, if you just encode individual characters, you don't achieve a lot of compression. So, so you don't use Huffman coding directly in document compression, right? So in fact, in early on, right? So if you are using compression programs in the 1970s and even in the 80s, Huffman coding was, if I remember correctly, there was a program called Compress on Unix, which would use Huffman coding in order to compress the file. And naturally, the results were unimpressive, right? So you probably get 30% reduction in size or 50% reduction in size if you're really lucky. But then we had these other set of algorithms which are able to work with much longer code words, not just individual characters, right? And so gzip algorithm is one of those. There is a series of algorithms that try, produce somewhat different techniques, but gzip implements this particular algorithm developed by Lempel and Zip, and it has this nice idea that you don't have to compute, the sender doesn't have to compute a code book and send it over to the receiver, but instead sender and receiver will both, use the same algorithm for constructing a code book on the fly, and because they do exactly the same thing, they will end up with the same code book even though they don't really, so that way the code book doesn't have to be transmitted. Okay? And the particular technique we talked about, you basically search in the preceding some number of bytes for and to see whether the current string has already appeared before. If it has already appeared before, then you have a compact encoding by pointing to that occurrence, right? Essentially, that's what you do. But if it doesn't occur, before, or it's too small that the pointer itself will take more space than putting the string in, then you just repeat that string, and you do that, and then at the second stage, you can use techniques like Huffman coding, so that the pointers themselves will be very compact. And gzip, of course, gives you a lot of speed, a lot of compression. So, how many of you know that gzip has this compression level parameter? So gzip has a parameter called compression level, which can be anywhere between 1 and 9, right? And what you will find is that gzip generally is not exactly a fast program if you try to use it on large files, right? So if you happen to have a video file you won't compress further because it's already compressed. But if you happen to have, let's say you're creating a backup of your entire directory and it happens to be several gigabytes, then applying gzip is quite slow. But by changing this, so the reason why it is slow in practice is because this search, right, finding the longest match for the current string, this is a slow process because, it's not enough. I mean, what is the current string? The current string, you don't know the length, right? So you can see the current string that you might find earlier could be of length 3 bytes, 4 bytes, 5 bytes, 100 bytes, right? How do you figure out what is the longest string that has been seen before, right? So you need to have some way of looking for that. So this is a search-intensive process, and that's why compression actually takes quite a bit of time. And what the compression factor allows you to do is to tell the algorithm, don't search, don't work too hard to find these matches, and then it can work much faster. So for instance, what I find is that if you use compression parameter 1, it ends up being lightning fast, and in fact you'll find that the compression, the amount of compression you achieve does not seem to be significantly effective. So maybe it will be off by 5%, right? So you have taken a file, compressed it to a third of its size or a fourth of its size. Okay, then instead of compressing it by 4 times, maybe you'll get 4.1 times compression. But in order to do that, you might end up spending 10 times the time. Right? So then, so again, because this search is expensive, the algorithm actually has allows you to control that search, and that way you can get things done faster, with possibly at the expense of some